All right, welcome back, everyone. So last week we talked about the sun as an introduction to the more detailed stuff that we know about stars, in particular just about the sun. But tonight we're going to expand our knowledge by talking about the properties of stars that we can measure, the patterns that we see amongst the stars. Essentially, when we look out into the universe and survey the stars, what do we see? So tonight we'll talk about a lot of terms and diagrams that will be very important for you to at least recognize, be able to recognize and be able to understand going forward as we talk about stars. So let's get started with tonight's quote by a very famous man, Neil deGrasse Tyson. He said, "When I look up at the night sky, I'm reminded that yes, we are part of this universe, we are in this universe, but more importantly, the universe is in us. Many people feel small because they're small and the universe is big, but we should instead feel big, knowing that our atoms came from those stars." Something I've said many, many times. All right, so when you look up at the night sky, for instance, at an image like this, you see that stars are incredibly numerous. There's so many stars, and those are just the stars that we can see with our unaided eye. If we add a telescope or even binoculars to the mix, then you can see even more stars that are too dim for our eyes to see. But one thing that should be readily apparent for you if you look up the night sky or even in images like this, the brightness of stars varies wildly depending on the star. You see in this image, there are some stars that are brighter than others. There's some stars that have different colors. So many of the stars here are kind of a blue-white. However, this star in particular is more of a reddish color, if you can see that through the zoom resolution. But these stars come in a wide variety of brightnesses and colors. And it's our job tonight to understand how those things are related, how we measure those things, and the patterns that we see. So when we talk about a star's brightness, we could talk about the brightness of the star on the night sky. However, that depends on distance between us and the star, as well as the actual amount of light it emits. So, for example, a 100-watt light bulb actually emits 100 watts of light. But it will appear much dimmer if I hold the light bulb, a football field away as opposed to right in front of my face. So the astronomy analogy to that is in the Winter Triangle, which is a relatively easy to spot asterism in the winter skies. You see image there in the top right. The triangle connects the stars Betelgeuse, Sirius, and Procyon in a triangle, which is very easy to see in the winter skies. Procyon and Betelgeuse, seen here, appear about the same brightness on the night sky, despite Betelgeuse emitting more than 15,000 times more light than Procyon. So that tells us that Procyon must be much closer to us to appear as bright as Betelgeuse. And so when we talk about brightnesses, astronomers distinguish between two types of brightness. First of all, we have the brightness of how a star appears in the night sky. That is its apparent brightness, where it will depend on both the intrinsic amount of light it emits as well as the distance to that star. The other type of brightness is quantity that we brought up last week when we talked about the sun, and that's the star's brightness in its absolute sense, its luminosity. How much light is it actually emitting, which does not depend on distance. So there are two different types of brightness here that we tend to talk about. Now, it's very important to realize that the apparent brightness of a star or any other bright source, a flashlight, a candle, an iPad screen, they all obey this inverse square law with distance. So this figure kind of gives you the idea. So we've got this light source at the very center of these concentric spheres. And so the same total amount of light must pass through each imaginary sphere surrounding that star. And if we focus on the light passing through the small square on the sphere located at 1 astronomical unit, 1 AU, we see that the same amount of light must pass through 4 squares of the same size on the sphere located at 2 AU, which therefore each square on the sphere of 2 AU receives only 1/2 squared, or 1/4 as much light as the square on the sphere at 1 AU. Similarly, going out to 3 AUs, we get 9 of those squares. So each square receives light only 1/3 squared, or 1/9 as much light as the square on the sphere of 1 AU. So generalizing, this inverse square law of light, that the amount of light over any particular area diminishes as you go out the distance squared, leads to a relationship between the apparent brightness, remember that's the brightness we see of the star on the night sky, and its luminosity, the actual amount of light the star is emitting, where the apparent brightness is equivalent to the luminosity divided by 4 pi times the distance squared. That 4 pi comes out of the fact that the surface area of the sphere is 4 pi d squared, so d is our distance. So in principle, we can always determine a star's apparent brightness by measuring the amount of light per unit area that we receive from the star, and then calculate a luminosity or a distance if we know the other quantity. So we can always measure an apparent brightness, hopefully. And if we know the distance, then we can get a luminosity. Or if we know the luminosity, we can get a distance. However, you should know by now it's not as simple as that. We can't just always get an apparent brightness. So, for example, we could measure an apparent brightness by using a detector that records how much light strikes it each second. So, for example, a detector would record an apparent brightness of 2.7 times 10 to the minus 8 watts per square meter for Alpha Centauri A, which is a very nearby star. It's one of the closest stars to us. But there are difficulties in getting that measurement because the detector's got to be properly calibrated. And for ground-based telescopes, we've got to deal with the Earth's atmosphere that's in the way that can actually absorb some of the light coming from Alpha Centauri A. And no detector can actually record the light of all wavelengths. No detector can record ultraviolet, optical, infrared, radio, X-ray, gamma ray, microwave. It can't do all that. So our detectors can only work in small ranges of wavelengths. Maybe you can only look at a portion of the optical light or a portion of the infrared light, for example. It can't get all of the wavelengths. So we actually will measure only, for instance, maybe the visible light apparent brightness or the X-ray luminosity. We won't actually measure the total luminosity or the total apparent brightness. Instead, we have to infer what those are after having measured the luminosity or the apparent brightness in many different ranges of wavelengths. So there are issues to just getting an apparent brightness and luminosity. We tend to just talk about them in small wavelength bands. And additionally, sometimes there's just dust in the way, very similar to the dust that floats around your living room or makes up a dusty road in the countryside. There's dust in space as well. And that has the effect of not only dimming the star, but also causing it to appear slightly redder than it actually is. So we've got to have a very good handle on where the dust is between us and the star. We're getting pretty good at that. But that is another, just one more problem on measuring brightnesses and luminosities here with stars. So here's your first little pop quiz question. So what do we need to measure in order to determine a star's luminosity? A, its apparent brightness and mass. B, its apparent brightness and temperature. Or C, its apparent brightness and distance. So take a moment to think about it. I'll tell you the answer in a moment. All right, the correct answer is C, the apparent brightness and distance. We haven't talked about mass or temperature yet, so that was hopefully a clue as towards the right answer. Now, we just talked about how we would measure apparent brightness using a detector here on Earth, a telescope, maybe a spectroscope. But how do we get that distance measurement? Well, the most direct distance measurement that we have relies only on simple geometry. And this technique is called stellar parallax, where we monitor the shifting of a nearby star with respect to the background stars every 6 months. So to get a handle on what parallax is, you can actually try this at home. So stick your thumb out at arm's length and look at it with respect to a background object, maybe a light switch on a wall or a lamp or something. Now, looking at your thumb, close one eye and then open the other one, close the other one, and go back and forth. And you'll see that your thumb appears to shift back and forth with respect to that further object. Now we can do the same thing with stars, except instead of using the very small space between our eyes, we'll actually use the position of Earth on either side of its orbit every 6 months. And we will see nearby stars. This doesn't work very well for really far away stars, but nearby stars, we'll see them actually shift in the sky with respect to further stars. So in this little diagram here, you can see we're looking at this kind of purplish, stars aren't purple, but this little purplish nearby star. And as we look at it in July, we see it on the right of these 6 background stars. As we look at it in January, we see it on the left of those 6 white background stars. And what we actually are measuring is this parallax angle P, which decreases the further the star is. If you were able to extend your thumb further than arm's length, you would see that the further you extend it, the smaller that apparent shift becomes. That's why it doesn't work for really far away stars, because the shift is just too small for us to detect. So by definition, the distance to an object with a parallax angle of 1 arcsecond, remember, that's a very small angular unit of measure. 1 degree can be split up into 60 arc minutes, and each arc minute can be split up into 60 arc seconds. So there are 3,600 arc seconds in 1 degree. So very small angular measure. So if an object has a parallax angle of 1 arc second, then its distance is defined to be 1 parsec, which is a unit, hopefully you've heard. It is, had been mentioned in Star Wars. Han Solo famously ran the Kessel Run in only so many parsecs, which is actually a correct statement. But we're not going to be using parsecs for the remainder of these talks. So it's actually easy to convert parsecs into light years. 1 parsec is about 3 1/3 light years. So we'll continue to talk about things in light years. But this is how astronomers get distances to nearby stars. We tend to use space-based telescopes for this. So back in the 90s, it was a telescope by the name of Hipparcos. Nowadays, the European Space Agency has launched the Gaia spacecraft, which is doing this very accurately. We've already a billion plus stars have been measured with very high accuracy. So we have very good estimates of distances here. All right. Finally, we do tend to state stellar luminosities in terms of the sun's luminosity. Remember, we talked about that last week. Is about 3.8 times 10 to the 26 watts. But that's all. But other stars can have much lower or much higher luminosities, and that's a lot of numbers to keep track of. So we just talk about in terms of the sun's luminosities. So for example, Proxima Centauri, the closest star to the sun, has a luminosity of 0.0006 solar luminosities, while Betelgeuse, that red star in Orion, which I think is actually right underneath that little sun right there, that is actually Betelgeuse in the background, has a luminosity of 120,000 times that of the sun. And stars come in a wide range of luminosities, from really, really small, 10 to the -4 solar luminosities, to 1 million solar luminosities. And we know that actually dim stars are far more common than bright stars. Now, I will mention this magnitude system. I will try my best to not talk about things in terms of magnitudes, but if you are into amateur astronomy and you want to go pick up some night sky observation books from your local bookstore, it will often talk about star brightnesses, not in terms of luminosity, but in terms of their brightness on the night sky and changing that into this logarithmic value that we call a magnitude. And this all came about because several millennia ago, some Greek astronomer named Hipparchus invented this magnitude system where the brightest stars are first magnitude, the next brightest are second magnitude, and so on. He only did down to 6 magnitudes because about 6 magnitudes is about as dim as our human eyes can see. But nowadays, we've got telescopes, so we could see brighter objects, we could see fainter objects, we could see fractional magnitude objects. So we've extended this and defined it precisely. So for example, here is a table of visual magnitudes for some of the objects that you might see in the sky tonight if you were to go outside tonight after watching this presentation. Obviously, you won't be able to see the sun tonight, but it is the brightest star in the night sky. Its magnitude is minus 26.7. Magnitude is sort of like golf scores, where the lower you get, the brighter an object is. So the moon will be the brightest object in the night sky tonight, magnitude of about minus 12. Jupiter will also be fairly bright, magnitude of about minus 2.5. And then you start to see some stars. Saturn will also be fairly bright tonight. Uranus, you'll have to be in a very dark sky spot to see it because 6 magnitudes is the naked eye visibility, and Uranus is just above that. You won't be able to see Neptune at all. You'll need a telescope to see Neptune. But I won't bring up magnitudes again, but if you go out and do your own observations, you might see magnitudes reported in books and online. So it's very important to at least show this to you. All right, so now let's talk about how we measure stellar temperatures. We just talked about how we measure stellar brightnesses. Now let's talk about how we measure stellar temperatures. So stars come in many different colors. And that tells us something about their surface temperatures. For instance, hot stars are blue and cooler stars are red. Just like fire. A campfire is a nice orangey reddish color. Meanwhile, if you've ever been in chemistry class or seen glass blowers, some of the fire that they deal with is white hot, blue hot. They're much hotter than the red fire of a campfire. And you can see in this image of stars, many different types of colors, a lot of red stars, but there are tons of blue stars in here as well. And so what astronomers have come up with, one way that we measure temperatures is by comparing a star's apparent brightness in 2 different colors of light. If a star is redder, then it must be cooler. If a star is bluer, then it must be hotter. So for example, here are 2 different stars. This is they are spectra that I put together. Remember, spectra, we're breaking up the light into different wavelengths, just like that rainbow image I often show. Like I keep saying, astronomers don't look at rainbow images like that. It's not that useful. So we like plots like these. And these blue and red bands are, for instance, 2 of the commonly used filters that we put on our telescope to just measure the light that comes through these 2 bands. And so you can see for the blue colored line, this blue star, if we take the stuff that's shaded in blue compared to the stuff that's shaded in red, there's clearly way more stuff in the blue. So the star is blue, so it must be pretty hot. Meanwhile, this red line here, if we compare the stuff that's in the blue rectangle versus the stuff that's in the red rectangle, there's more stuff in the red rectangle, which means that it must be more red, meaning it's cooler than this blue star. And that's true. That's how we get a lot of temperatures for stars. An alternative way, if you have the time and the equipment necessary, you can actually just take the spectrum of a star. That's a very accurate way of getting a star's temperature. And so you can classify stars by their spectral type. So here you see a bunch of different rainbow spectra for different types of stars. And the different types of stars are labeled here. O, B, A, F, G, K, M. Those are the spectral types. And you can see that there are different features that pop up in these spectra. So as we go from the O stars, when you look all the way over here at the red, this dark line that pops up, this is the H alpha, the strongest line of ionized hydrogen. It gets weak and then stronger once it reaches into the A stars, and then weaker again to where it's not even visible. This can be thought of as a temperature relation, where O stars are so hot that hydrogen cannot do anything with light. It can absorb hardly anything. It gets cooler, but it's still hot enough for hydrogen to be ionized, but more strongly ionized here. Less strongly ionized, I apologize. And then as we get into G, K, and M, the stars become so cool that even hydrogen isn't ionized. Contrast it with, on the bottom are labeled a bunch of different molecules. So the one in the yellow is sodium iodide, where O, B, A, and F stars are too hot for molecules to form. But as we get to G, K, and M stars, they get cooler and molecules are more stable. Now, you may have noticed this really weird order. It's not at all alphabetical. So astronomers have come up with many mnemonics to remember the order of these spectral types. The most famous one is, oh, be a fine guy or girl, kiss me. Another one that I've seen recently is only boring astronomers forget generally known mnemonics. You, of course, come up with your own. When I took an Astronomy 101 class in undergrad, our professor asked us to come up with our own mnemonics, and one of my friends came up with Obama bans all Obama bans all free guns, KKK mad. I thought that was hilarious. Ignore the politics of that statement. I thought that was hilarious. So I'm sharing it with you now. Now, the reason this isn't in alphabetical order is a bit of a history lesson. And I did want to bring this up because it is some wonderful astronomers who came up with this. So back in the late 19th century, astronomical research didn't really pay well. And so the astronomers of the day were people who had family wealth and they could afford to, not go get a trade job or work in the finances and be able to spend their time staring up at the night sky. And one early pioneer was a man named Henry Draper. But he died in 1882, and his widow made a lot of donations to the Harvard College Observatory for the purpose of building on Henry Draper's work. And so the observatory director, Edward Pickering, used the gifts to improve the facilities and hire a bunch of assistants, whom he called computers. Back in the day, women were very cheap to pay. And so all of his computers were women. Women were doing all of the work here. Thankfully, the names of these women have not been lost to time. I'll tell you a few of their names in a moment. But this was looked down upon by the other astronomers, by other Harvard colleagues. They were often referred to not as his computers, but as Pickering's harem. Very degrading. But these were very well-educated women. They had studied physics or astronomy at Williams colleges like Wellesley and Radcliffe. Harvard wouldn't allow them to enroll as students and wouldn't allow them to be faculty. So this was the first kind of entrance into the professional world of astronomy at Harvard and in the much wider astronomical community. Now, three of these women are important for our discussion tonight. One of the first computers was a woman named Williamina Fleming. Following Pickering's suggestion, Fleming classified stellar spectra according to the strength of their hydrogen lines. So type A had the strongest hydrogen lines, type B for slightly weaker, and so on all the way to type O with the weakest hydrogen lines. And so Pickering published Fleming's classifications with her name attached. It was very big of him. More than 10,000 stars in 1890. And in general, as more stellar spectra were obtained and the spectra were able to be studied in more detail, it became clear that the classification scheme based solely on hydrogen lines was inadequate. So ultimately, another woman, Antonia Maury, built upon what Fleming did, tweaked the little things, but it really fell to just an amazing woman, Annie Jump Cannon, to realize that the spectral classes fell into a natural order, but not the alphabetical order based on the strength of the hydrogen lines. Moreover, she found that some of the original classes actually overlapped and got rid of them. And so she condensed a large set of alphabetical classes going from like A to O into the OBAFGKM sequence that we know today. Annie Jump Cannon was also deaf. She classified over 350,000 stars in her lifetime. She became so good at it that she could classify a star at just a moment's glance of its spectra. And she became the first woman ever awarded an honorary degree by Oxford University. And in 1923, the League of Women Voters named her one of the 12 greatest living American women. However, no one knew why the classification system followed OBAFGKM. And many astronomers guessed incorrectly that the sets of spectral lines indicated different compositions for the stars. But the correct answer, that the stars are made primarily of hydrogen and helium, and that it's a star's surface temperature that determines the strength of its spectral lines, was discovered at Harvard Observatory by another woman, Cecilia Payne-Gaposchkin. And she showed that the differences in the spectral lines merely reflect changes in the ionization level of emitting atoms, which we talked about a while ago, twice by now. So for example, O stars have weak hydrogen lines because at their high surface temperatures, nearly all of their hydrogen is ionized. And without an electron to jump between energy levels, they can't emit or absorb a particular wavelength of light. At the other end of the sequence, the M stars are cool enough for some stable molecules to form, explaining those strong molecular absorption lines. She described, Cecilia Payne-Gaposchkin described all of this in her thesis in 1925, and her thesis was used as like a seminal textbook for many decades on the subject. So tons of women did all of this work, and they really should be thanked. They did an amazing job, and astronomers still use all of their work to this day. So moving on from stellar temperatures, how do we actually measure masses of stars? Well, masses are really only measurable for star systems. Mass is a very hard quantity to measure. And you can't do it with individual stars because still the most reliable method of measuring masses is using Kepler's laws, Newton's extension of Kepler's laws. But Kepler's law, and you need orbiting objects to get those numbers. So there are different types of binary star systems. Of course, star systems can come in triples, quadruples. We've measured up to septuple star systems. That's 7 star systems all orbiting each other in some complex way. But we'll talk about the binaries just for now. Visual binaries are pairs of stars that we can see distinctly. So for example, one of the stars in the Big Dipper is a visual binary. Here's a little video I made of me zooming in to Mizar. That's the star's name. You can see as I zoom in closer, it actually splits into 2 stars. It's a visual binary. We also have spectroscopic binaries where they are identified purely through their Doppler shifts in their spectral lines. I'm not going to go into that. And then we have eclipsing binaries where we got pairs of stars that, just like eclipsing exoplanetary systems, where one star will pass in front of another star, dimming the total system's brightness, and then pass behind the other star, dimming it a bit more because they're blocking light. So we get masses of binary systems, and then we can extrapolate to what, depending on the spectral type of the stars in those binary systems, you can extrapolate to what masses of single stars must be like. But we can't directly measure the masses of single stars, just for star systems. All right, so now we come to a very, very, very important diagram in astronomy, and that is the HR diagram, named for the initials of the Danish astronomer Einar Hertzsprung and the American astronomer Henry Norris Russell, so Hertzsprung-Russell diagram, who built upon the work of Annie Jump Cannon and the other computers at Harvard. And they both independently decided to make graphs of stellar properties by plotting luminosity on one axis and spectral types on another. And magically, the stars arrange themselves into these different groups. And so let's orient ourselves, before we talk about the patterns here, let's orient ourselves with what is happening in this diagram. So on the left vertical axis is the luminosity of the star in solar luminosities. So one solar luminosity, that's the sun, and indeed, if we follow it to the right, I put a yellow circle there for where the sun falls on this diagram. Okay, so 100,000 solar luminosities .00001 solar luminosity. So really, really dim at the bottom, really bright at the top, intrinsically bright. We're going to ignore the right vertical axis, that's magnitudes. We're not going to talk about magnitudes. On the bottom is the color of the star, where stuff to the left is blue, stuff to the right is red. That's the color as determined from looking at the stars, how the stars light through two different filters on a telescope, a blue filter and a redder filter, just like I showed you before. On the top horizontal are two things. So at the very top is the spectral sequence. O stars to the left, then go BAF, GK, M stars to the right. And as we just discussed, those spectral types correspond to temperature. So hot stars to the left, 30,000 Kelvin O stars, all the way down to just 3,000 Kelvin M star. So hot stuff to the left, cooler stuff to the right. So we can see from the sun's position on this diagram, it has a luminosity of 1 solar mass, a color of just slightly blue. It's a blue-white. We color it yellow, though. And a temperature of about 6,000 Kelvin. It's a G-type star. And we can see that there are several different patterns here, different ways the stars have arranged themselves. So most stars fall right along this diagonal, which is called the main sequence, because it is the main sequence in this diagram. Going from hot, very luminous stars, very bright stars, very blue stars up at the top left, to cooler, dimmer, redder stars at the bottom right. And our sun falls along this main sequence. Okay. There's another group. The stars at the top are supergiants, since regardless of their temperature or their color, they are very hot. And they are actually very large as well. They are actually very big. These are called supergiants. Then there's another cluster right below them, kind of tilted here. These are the giants, which are somewhat dimmer and somewhat smaller. And then all the way down at the bottom, below the main sequence, are small stars. They're very small in radius, but they are very hot. A lot of them are 10,000 Kelvin, and most of them are very blue. These are white dwarfs. Okay, so different groups. We've got the main sequence that extends diagonally, where most stars live. We've got the sparse group of supergiants at the top. We've got some dimmer, but still bright and large giants, and then some very dim, but very hot white dwarfs at the bottom below the main sequence. Okay. Astronomers also distinguish, make a distinction between luminosity classes, and that's the purple lines that you see here on this particular plot. So Roman numeral 1 are supergiants, Roman numeral 2 are bright giants, Roman numeral 3 are giants, Roman numeral 4 are subgiants, and Roman numeral 5 are main sequence stars. And then we typically just say WD for white dwarfs. Very creative, I know. So combining luminosity classes and spectral types, if you know both of those for a star, then you can actually specify, that completely specifies where a star falls on this plot. So a full classification would list both the star spectral type, that OBAFGKM, and the star's luminosity class, Roman numerals 1 through 5. So for example, the sun is a G25 star, where the G2 tells us that it's a yellow-white star, and the V, the 5, tells us it's on the main sequence. I forgot to mention that we split the spectral types into Arabic numerals, 0 through 9, just to give us a little bit more distinction. Rather than just saying a G5, we say a G25. So it is slightly cooler than a G05, slightly hotter than a G95. That's the idea that we're going for. Betelgeuse up here is an M21 star. So we know that it is a cool star because of that M2 part, and we know that it's red, M, once again. And then that 1 tells us it's a supergiant. So it should be at the red and cool end of the HR diagram and high up, has a lot of luminosity because of that Roman numeral 1. Meanwhile, Proxima Centauri is an M55 star. So once again, cool and red because of the M5 part. But that Roman numeral 5, the V, tells us it's on the main sequence. And because we know the shape of the main sequence, we must know that it is also a very dim star. It's at the bottom right corner. So you can see we can completely specify where a star is based on its spectral type and luminosity class alone. All right, there are some more patterns that are harder to see on the HR diagram. Stellar masses are actually represented here along the main sequence, where they decrease down the main sequence. So high mass stars are at the top left, lower mass stars are at the bottom right. And we know that mass is the most important attribute of a hydrogen fusing star, since it determines that balancing point at which energy is released by fusion and matches the energy lost from a star's surface. Mass is the most important attribute for a star. Knowing a star's mass pretty much tells you everything you need to know about that star. So for example, a 10 solar mass star has about 10,000 solar luminosities. And more massive stars also have higher temperatures on average, and less massive stars have lower temperatures on average. There are always going to be some exceptions to the rules. Another trend, once again following the main sequence, is that time spent on the main sequence increases down the main sequence. So these really hot, really bright, really massive stars at the top left aren't going to live long, because that mass determines, although it determines how much hydrogen a star has initially to use throughout its lifetime, the luminosity determines how fast the star is going to burn through all that hydrogen. So these really luminous, really massive stars are going to burn through their hydrogen so fast. So a star with 10 solar masses may have 10,000 solar luminosities, but it's only going to live for 10 million years. So that's a blink of an eye on cosmological timescales. Meanwhile, at the dimmer end of the main sequence, where they're lower mass, so they don't have much hydrogen to begin with, but they're very dim. So they're going to burn through that amount of hydrogen on very, very slowly. So even though a star of just 3/10 of a solar mass has 1/100th of a solar luminosity, it will live for 300 billion years, longer than the age of the universe. So these really low mass stars that were created at the beginning of the universe are still around today. Meanwhile, the high mass stars that were created at the beginning of the universe died out a long, long time ago. So these are all the different patterns on the HR diagram, at least for the main sequence. So here are 3 questions. I'm going to give you some time to answer this. Definitely please pause the video and think about these questions. So first one is, which of these stars has the coolest surface temperature? An A star, an F star, or a K star? Then, which of these stars is the most massive? A main sequence A star, a main sequence G star, or a main sequence M star? And then which of these stars has the longest lifetime? A main sequence A star, a main sequence G star, or a main sequence M star? So pause the video, go backwards if you need to, if you want to look at the HR diagram for reference. But definitely pause the video and think about your answers. All right, now that you've got your answers, here are the correct ones. So which of these stars has the coolest surface temperature? A K star. It's all the way there to the right on the HR diagram. And as you go to the right, you get to the cooler stars. Which of these stars is the most massive? A main sequence A star. Mass increases towards the left along the main sequence. And out of these spectral types, the A is the furthest one to the left. And then which of these stars has the longest lifetime? A main sequence M star, because it's the furthest to the right. Remember, stellar lifetimes increase as we go towards the right on the main sequence. So go back and review if you don't fully understand. Definitely leave a comment or message me, and I will try and help you with that. Because this is all going to be very important as we continue to talk about stars over the coming weeks. Now, we just talked a lot about main sequence stars, but there are other groups on the HR diagram that aren't main sequence, and those are the giants and the supergiants. So those giants and supergiants in the upper right corner of the HR diagram are actually huge. Those names are very accurate. Betelgeuse, that red star in the top left corner of that hourglass shape of Orion, is a supergiant star. that's nearly 1,000 times the size of the sun, while Aldebaran, the bright red eye of Taurus the Bull, is a giant star almost 50 times as large as the sun. So these are really, really big. You see some things to scale here. The sun is just that small yellow dot here. Betelgeuse, you can't even see the full star on this image. And Aldebaran, you can see right there, is definitely much larger than the sun. Now, both of these types of stars are different from the main sequence because they are no longer fusing hydrogen in their cores. And they're essentially going through an energy crisis to stop themselves collapsing. They are burning anything they can. Just like a pyromaniac child will throw anything into the fireplace just to see the fire burn. These supergiants and giants are the pyromaniac children of the universe, where they're just trying so hard to keep the flame alight. We will talk about what those fusion options are for them in the coming weeks. But eventually, when they do run out of fuel, some of them, not all of them, some of them will turn into white dwarfs, moving all the way to the very bottom of the HR diagram, where they're no longer doing any fusion of any material, but they're just radiating away leftover heat, just like a warm cup of coffee left in a room to sit, where you come back and you realize, oh, dang it, I didn't drink the coffee. So that's what white dwarfs are. Now, briefly, I just want to mention some star clusters, because star clusters are very useful for astronomers for two big reasons. So first of all of the stars in the cluster lie at about the same distance from Earth. So if we know the distance of even one of the stars, we've got the distance for all the other stars, and we can easily calculate luminosities from their apparent brightnesses. And all of the stars in the cluster formed at about the same time, within a few million years. So we get to see how stars evolve together. And so star clusters come in these two basic types: open clusters and globular clusters. Open clusters are, open clusters are always found in the flat disk of the Milky Way galaxy, of any sparkle galaxy, and they tend to be very young. They tend to be just maybe a few million years, a few 100 million years old. This image is the image of one of the most famous open clusters on the night sky, the Pleiades. It's a very prominent open cluster that you can actually see with your naked eye in the constellation of Taurus. It's sometimes been called the Seven Sisters, although only 6 of the cluster's thousands of stars are easily visible. Other cultures have had names. In Japan, it is called Subaru, which is why it is the logo for the Subaru cars. You see that from the cars. Open clusters tend to have several thousand stars and are relatively small, just about 30 light years across on average. And once again, the Pleiades is the most famous example. In contrast, globular clusters are not found in the disk of the galaxy, but in the spherical halo surrounding the galaxy. We'll talk about all this stuff once again when we get to galaxies. And they contain some of the oldest stars in the universe. Usually, 11, 12 billion years old. They contain more than 1 million stars in a ball, typically between 60 to 150 light years across. This is an image of the globular cluster Omega Centauri, also known by its new general catalog number 5139. And it's the largest globular cluster in the Milky Way, containing about 10 million stars. In fact, we think it is actually the remnant core of a dwarf galaxy the Milky Way has swallowed up in the past. But seriously, if you were living on a planet inside a globular cluster, you would look up and you'd be bathed in light constantly. Just so many stars surrounding you at all times. Now, the reason these clusters are important is because we can get ages for them very easily. So if we plot the stars of a cluster on an HR diagram, we can look for where stars will start to peel off the main sequence. And that point where they peel off the main sequence is creatively called the main sequence turn-off point. So here you can see a bunch of different open clusters here. So once again, on the vertical is some measure of brightness. Here it is a magnitude, but just remember, bright towards the top, dim towards the bottom. And then on the horizontal is a color. So blue, hot stuff towards the left, red, cold stuff towards the right. And if we look at the line marked Pleiades. You can see that it has a main sequence, but it turns off at one particular point. And that turnoff happens around the spectral type of a B6 star. And B6 stars, from our computer modeling and our understanding of stars and stellar lifetimes, B6 stars have a lifetime of around 100 million years. So that must be the age of the Pleiades. For Omega Centauri, which is a huge globular cluster, its turnoff indicates an age of 11.5 billion years. And you can see other open clusters here as well. So the Coma cluster, the Hyades, Perseps, also known as the Beehive cluster, those have turnoffs maybe 10 to the 9, 10 to the 9.5 years. So, you know, what's 10 to the 9? A billion years. H and Chi Persei, the double cluster, 10 to the 7 years. So just 10 million years. That's how old those clusters are. This is a very useful technique, and undergrad astronomers learn about this technique and use it in homework assignments or whatnot. It's still used widely to this day. So that's why star clusters are important. And I did want to mention there are a few clusters you can go out and see. If you're in a dark sky spot, I picked these because they should be visible to the naked eye under good conditions, though you might need some binoculars or even a telescope depending on your local sky conditions. So tonight, if you're going to go outside and you look at the southeast, if you can find the constellation of Ophiuchus, and this is where having an app on your phone or an astronomy book, night sky observing guide with you would help. You can look for the Summer Beehive cluster, which should be just off this little star in Ophiuchus, also known as Poseidon's Trident cluster or the Black Swallowtail Butterfly cluster. You should be able to see that with your naked eye. This is what it looks like. If you can barely see in this image, it is in the middle of the image. Those sort of blue stars there, that is the Summer Beehive cluster. And there's that one bright star in Ophiuchus that you can use as a reference point. There's also a globular cluster visible. So just slightly more east is the Great Star Cluster in Hercules, the Hercules Globular Cluster, also known as Messier 13 in Charles Messier's catalog. You can also see this with visible to your naked eye, although you gotta be really good sky conditions. You gotta be in a dark sky spot. So you'll probably need some binoculars or a telescope to help you out with this one. But if you can spot it, it's a very beautiful, beautiful sight to behold. That is what it looks like through amateur astronomy's telescope. So definitely go out and try and see these star clusters tonight. If you are watching this presentation anytime in the next week or so, you'll be able to see these. So that is it. Next week, we will talk about how stars are born, how stars are made. And so I will see you next week. As always, let me know if you have any questions or problems, understand anything. I would love to help. Make sure you like, comment, and subscribe, and do all the fun YouTube things. And otherwise, I will see you next week.